G'day folks, and welcome to the Crystal Field Theory Idea Experiment pre-lab video. In this idea experiment, we're going to investigate what colour can tell us about the d orbitals in cobalt complexes, also known as coordination compounds. Not only will we use the naked eye to observe colour, but we'll use spectrophotometry to measure the absorbed colour by these sorts of materials. So the aim of today's experiment is going to be A, to synthesize some cobalt coordination compounds, B, to use spectrophotometry to investigate how the absorbed light yields the colour that we see using the naked eye, and the third aim of the experiment is to actually take these spectra and use it to recreate something called the spectrochemical series. But first, a bit of background. Just a little example of materials which give us colour. Chemists often use a desiccator, a piece of glassware which looks a bit like this, to keep materials dry. Not only can a vacuum be used to evacuate all the moisture out of this kind of container, but you can also put a desiccant into the base of the unit, such as these cobalt chloride crystals. In this case, we're using cobalt-2 chloride crystals. This is a cobalt coordination compound. Actually, when it's still in this form, we can say that the material is generally pretty dry. However, over time, this coordination compound is very good at reacting with water to give this material here. And it has a very different colour. The cobalt metal centre is still in a 2+ state, but the ligand on that metal centre has changed. And of course, you've probably seen that all sorts of different transition metal coordination compounds exhibit all sorts of different colours. In this table here, we can see that on the left-hand side, for all sorts of different metals which have the same ligand, you will observe all sorts of different colours. On the right-hand side, you can see that for at least 4 of those, we're using cobalt 3+, with the overall charge changing as we change the ligand. And sure enough, the colour of that material changes as well. The colour of the aqua complexes arises from the absorption of visible light due to D to D transitions. But how is this possible? Aren't the d orbitals with the same principal quantum number n degenerate? In other words, aren't they equal in energy? Well, let's have a bit of a closer think about the d orbitals in our transition metal complexes. And hopefully you recognise these shapes here. These are the 5 d orbitals: dxy, dyz, dxz, and dx squared minus y squared, and dz squared. Now let's consider the ligands on an octahedral complex lying on the x, y, and z axes. Think back to the directionality of the d atomic orbitals, and what you should see is that some of these ligands actually lie perfectly on the axes, just like 2 of the orbitals that you can see here. The dx squared minus y squared and dz squared have their electron density lying right on those axes. We also have ligands lying right on those axes. In other words, we have greater ligand to d electron repulsion if electrons are in the orbitals that point at those ligands, that is the dx squared minus y squared and dz squared, rather than those between the axes, the dxy, dyz, and dxz. So in a bare atom or an ion, we can see that we have 5 degenerate d atomic orbitals. However, once we set up what we call the crystal field, we get a splitting of these d orbitals. Because the dx squared minus y squared and dz squared are pointing directly towards the ligand where there's additional repulsion, it destabilizes those orbitals and raises them in energy. Correspondingly, these are now higher in energy than the other 3 d atomic orbitals. Therefore, we have a difference in energy. The spectrochemical series is actually a series that we can create when we line up the effect that different ligands have on the size of this energy splitting. And you can see down the bottom end of the spectrochemical series, we have predominantly the halides. So this ligand does not have a huge effect on this splitting energy. At the other end, we can see that cyanide and carbon monoxide, up the other end, are strong field ligands. They have a large impact on this energy. When one of these coordination compounds absorbs a photon whose energy perfectly aligns with this difference in energy, we can actually promote an electron from the lower d orbitals to one of the upper d orbitals. And we call these d to d electronic transitions. So if we study these d to d electronic transitions, we can actually learn about the crystal field splitting. We call the magnitude of this splitting delta oct, or delta O, with that small o standing for octahedral in this case, because we're talking about octahedral complexes. If the ligands in the system are from the low end of the spectrochemical series, we say that they're low field ligands. We'll see that this is a small energy gap. As we move to the other end of the spectrochemical series, we can see that the crystal field splitting, however, increases. And of course, this is why we saw all of the different rich and lovely colours of different transition metal coordination compounds. Because as we change the ligand system, we change the energy gap, and therefore we're changing the wavelength of the light which is being absorbed. In other words, we're changing the colour of the system. And of course, the colour is what we detect using the human eye. And what we're really seeing there is, if you like, the colour which is not being absorbed by the material. So how do we work out what's being absorbed by the material? And that's where we turn to UV-Vis spectrophotometry. In this experiment, we're going to be performing a wavelength scan. In this kind of experiment, we can scan across the wavelengths of the visible spectrum and measure which wavelengths are being absorbed. So you'll put your sample in the machine, presumably get some sort of profile which looks a little bit like this. And what we'll be focusing on is the point of maximum absorbance, what we often call lambda max, lambda being the Greek symbol which we use to denote wavelength. And even though lambda max doesn't line up perfectly with delta naught, it's pretty close. And so for this first year experiment, it's a pretty good approximation, which we can actually use to measure that energy splitting, or that crystal field splitting energy. One final comment is be on the lookout for changes in the spin. If we follow the Aufbau principle, we always get a low spin configuration for our d electrons. And when we say low spin, what we're really saying is the lowest number of unpaired electrons. Depending on what sort of ligand system you're using, though, you can sometimes get a high spin arrangement. And that is when the splitting is actually quite small, and the spin pairing energy causes some electrons to be automatically promoted to the higher levels, thus to minimize electron repulsion. Anyway, that's probably enough to get you going for the pre-lab quiz and to start thinking about this experiment. So let me just mention what those aims are of the experiment once again. Aim 1, we're going to synthesize some cobalt coordination compounds. 2, we're going to use spectrophotometry to measure the crystal field splitting in each of those different cobalt complexes. The final step is we're going to get you guys to reconstruct the spectrochemical series based on your results. Good luck with the experiment.